the 125% multiplication factor is applied to continuous loads such as SPOs, due to the expectation of extended operation. This factor is designed to address the potential impact of sustained power draw on the electrical system. When seeking to avoid altering the service, consider utilizing a demand factor for the SPO. Demand factors serve to diminish the calculated load based on the assumption that not all loads will operate simultaneously at their maximum capacity. For SPOs, a demand factor of 70% is frequently employed. Instead of multiplying the SPO load by 125%, a multiplication by 70% would be applied. Note that the acceptability of demand factors is not universal among electrical codes and authorities. Consulting the local electrical inspector is crucial to ascertain the appropriate methodology for calculating the load for SPO in the specific location. Electrical load calculations are a fundamental aspect of electrical system design and safety. They determine the required capacity of the electrical service, feeders, and branch circuits. Accurate load calculations are essential to prevent overloading, which can lead to overheating, insulation breakdown, and potentially fires. The National Electrical Code, or NEC, provides detailed guidelines for performing load calculations. The NEC specifies various factors and methods to account for different types of loads, including continuous loads, non-continuous loads, and loads with intermittent operation. Continuous loads are defined as loads that operate for 3 hours or more at a time. Due to the sustained power draw, continuous loads are subject to 125% factor to ensure that the electrical system is adequately sized to handle the prolonged demand. This 125% factor is applied to the branch circuit, feeder, and service conductors. SPOs are often considered continuous loads due to their typical usage patterns. Users may spend extended periods of time in a SPO, resulting in continuous operation of the pump, heater, and other electrical components. This continuous operation necessitates the application of the 125% factor to the SPO's electrical load. The 125% factor is applied to the nameplate rating of the SPO's electrical equipment. The nameplate rating indicates the maximum power consumption of the SPO. Multiplying this value by 125% provides a larger calculated load that accounts for the sustained power draw during continuous operation. This larger calculated load ensures that the electrical system has sufficient capacity to handle the SPO's demand without experiencing overloading or overheating. In some cases, it may be desirable to avoid applying the 125% factor to the SPO's electrical load. This may be due to concerns about increasing the service size or exceeding the capacity of the existing electrical system. In such situations, a demand factor may be considered. A demand factor is a multiplier less than 100% that is applied to the calculated load. Demand factors are based on the assumption that not all loads will operate simultaneously at their maximum capacity. For example, a demand factor of 70% indicates that only 70% of the connected load is expected to be in operation at any given time. Demand factors can be used to reduce the calculated load, potentially avoiding the need to increase the service size or upgrade the electrical system. However, it is important to note that demand factors are not universally accepted by all electrical codes and authorities. The NEC provides specific guidelines for applying demand factors, and these guidelines may vary depending on the type of load and the specific application. For SPOs, a demand factor of 70% is commonly used. This demand factor is based on the assumption that the SPO will not always be operating at its maximum capacity. During periods of non-use or reduced usage, the SPO's power consumption may be significantly lower than its nameplate rating. Applying a demand factor of 70% takes this reduced power consumption into account, resulting in a lower calculated load. When considering the use of a demand factor for a SPO, it is essential to consult with the local electrical inspector. The electrical inspector is responsible for enforcing the electrical code in the specific jurisdiction. The electrical inspector can provide guidance on the acceptability of demand factors and the specific requirements that must be met. In some jurisdictions, the electrical inspector may require additional documentation or calculations to support the use of a demand factor. This documentation may include historical usage data, load monitoring reports, or other evidence that demonstrates that the SPA's actual power consumption is lower than its nameplate rating. If the electrical inspector approves the use of a demand factor, the calculated load for the SPA can be reduced accordingly. This reduced calculated load may allow the existing electrical system to accommodate the SPA without requiring an upgrade. However, it is important to ensure that the reduced calculated load is still sufficient to handle the SPA's actual power consumption under all operating conditions. Overloading the electrical system, even for short periods of time, can lead to overheating and potential hazards. In addition to consulting with the local electrical inspector, it is also advisable to consult with a qualified electrician. A qualified electrician can perform a thorough evaluation of the electrical system and provide recommendations on the appropriate load calculation methodology. The electrician can also assess the capacity of the existing electrical system and determine whether any upgrades are necessary. When performing load calculations for SPAs, it is important to consider all of the electrical components that will be connected to the circuit. This includes the pump, heater, lights, and any other accessories. Each of these components has a specific power consumption rating, which must be included in the load calculation. It is also important to consider the voltage and amperage requirements of the SPA. The voltage and amperage ratings must be compatible with the electrical system to ensure safe and reliable operation. The NEC provides detailed tables and guidelines for determining the appropriate wire size and overcurrent protection for SPA circuits. These tables and guidelines take into account the voltage, amperage, and conductor type. It is essential to follow these guidelines to ensure that the SPA circuit is properly protected from overloading and short circuits. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current in the event of an overload or short circuit. These devices protect the electrical system from damage and prevent potential fires. The overcurrent protection device must be sized appropriately for the SPA circuit. If the overcurrent protection device is too small, it will trip frequently, interrupting the SPA's operation. If the overcurrent protection device is too large, it may not trip in the event of an overload or short circuit, potentially leading to damage or fire. In addition to load calculations and overcurrent protection, proper grounding is also essential for SPA safety. Grounding provides a path for fault current to return to the source, minimizing the risk of electric shock. The NEC requires that all metal parts of the SPA, including the pump, heater, and metal enclosure, be properly grounded. Grounding electrodes, such as ground rods or ground plates, are used to establish a connection to the earth. These electrodes provide a low impedance path for fault current to flow back to the source. Ground fault circuit interrupters, or GFCIs, are also required for SPA circuits. GFCIs are designed to detect small imbalances in current flow, which can indicate a ground fault. When a ground fault is detected, the GFCI quickly interrupts the circuit, preventing electric shock. GFCIs are typically installed in the SPA's electrical panel or in a weatherproof enclosure near the SPA. Regular testing of the GFCI is essential to ensure that it is functioning properly. Test buttons are provided on the GFCI for this purpose. Pressing the test button should cause the GFCI to trip, indicating that it is working correctly. If the GFCI does not trip when the test button is pressed, it should be replaced immediately. In summary, performing accurate load calculations is essential for ensuring the safe and reliable operation of SPAs. The 125% factor for continuous loads must be considered, and demand factors may be used to reduce the calculated load in certain situations. Consulting with the local electrical inspector and a qualified electrician is crucial to determine the appropriate load calculation methodology and ensure compliance with all applicable codes and regulations. Proper grounding and GFCI protection are also essential for SPA safety. Firstly, continuous loads, like SPAs, require a 125% multiplication factor due to the sustained operation, addressing the potential impact of continuous power draw. Secondly, when avoiding service changes, a demand factor can be considered. This reduces the calculated load, assuming not all loads operate simultaneously at maximum capacity. Thirdly, a 70% demand factor is commonly used for SPOs, multiplying the load by 70% instead of 125%. Lastly, the acceptability of demand factors varies. Consultation with the local electrical inspector is crucial to determine the appropriate load calculation methodology for SPOs in its specific location.